All right. So we're going to start discussing chapter 9, which is the control stage. Yeah, for power supply, including DC to DC converter, I'm gonna use a buck converter, a buck converter as an example. So let's say I have a buck converter, right? That looks like this. Here's our load, right? Here's our output. Of course, is our input right here. And the transfer function that we have for a buck converter for CCM, continuous conduction mode, is that V out average is equal to duty cycle times V in, right? And duty cycle is equal to T on over T times V in, right? And T on being the conduction time of the switch. So we actually send a signal, like a pulse signal to the switch right there, right? When the signal is low, it's going to be off. The switch is going to be off. Let's call it switch number switch S1. So when the signal is low, the switch is off. When the signal is high, the switch is on, right? So T on corresponds to the conduction time of the switch right there. And there's T off right here, right? And we learned from EE410 that since D is equal to T on over T, therefore T on is equal to dt, and T off, right? T off should be, if I go back to this pulse and this time segment right here, from here to here, right? That's the one period. Then T off must be T minus T on, right? The entire period minus T on, that's T off. And so T on by itself is dt. So therefore, T off is equal to 1 minus D times T, right? Okay. So then back to this buck converter, right? So V out is equal to duty cycle times V in. So again, duty cycle is a signal that we apply to the switch. So therefore, this is what we do right there, right? We have duty cycle sent to the switch, just like that. So depending on how much duty cycle you put into the switch, that would determine V out. Of course, given V in, right? So given V in and duty cycle, then you get the output voltage, right? Now, if you just do this in real world, this is not going to work, right? Reason being, we have variations either at the input as well as the output, right? And so imagine if there is a change in the input voltage, right, in real world, right? You're going to have changes in the input voltage. Then in order to keep the same output voltage, you have to change duty cycle, right? And this input voltage, the change in input voltage could be continuous. That could be something that keeps going on and on, right? Keeps changing, basically ripple, like a ripple, right? So if that's the case, then imagine if you don't have any control, like automatic control of the duty cycle, then you have to keep the duty cycle manually, right? You have to keep changing the duty cycle manually in order to give us the same output voltage, right? The bottom line is that in order for us to be able to regulate the output voltage, we need a way to somehow control the duty cycle automatically upon any changes, not just at the input voltage, but also at the load, right? So the same thing happens when the load changes. When the load changes, then the amount of current flowing through the circuit will change as well. And in real world, we're going to have drops, right, across the inductor, drops across the diode. That would also change with respect to the load demand, with respect to the current that flows from the input to the output, right? So depending on the variation on the load as well, the output voltage will change accordingly. So how do we keep the output voltage constant? By having the feedback controller, right? So we can have a way to watch the output voltage, right? And then process that signal, right? So that we can output the duty cycle, the proper duty cycle. This is what we call controller, right? So then, so that's the basic block diagram of the controller. So in real world, that's what you need to have. But you also need to have controller, not just the buck converter, but also not just the power stage. So the one in blue is the power stage, but also you need the controller stage, right? So any DC to DC controller or DC to DC converter or linear regulator, you're gonna have both power stage and controller stage. Okay. Now, again, this is just a block diagram, but then how do we do it in the actual circuit? For DC to DC converter, I'm going to erase this, okay? The way we do this is simply by, the most common way is to use voltage divider, right? Voltage divider, and then voltage divider is actually a perfect fixer to use for voltage, right? And then right here, so you have our top, our bottom, right? And as you know, any change in this node right there will be reflected by the same percentage at that node, right? So if I call this V mid, right? So V out, any change in the V out, it will also be reflected by the same amount of percentage by or at V mid, right? And this is what we use to actually process the signal. This is what we use to actually control the duty cycle, right? How? So the actual sample, this is basically V out prime, right? I can call it V out prime, which is a sample output voltage, which is the same as V mid. I could use that information, right? And then compare it with a reference voltage, right? So this reference voltage defines the desired output voltage, right? And typically, reference voltage is constant voltage, of course, right? It's a supply voltage, just like that one. And the value of it actually varies depend on the controller that you choose. But let's say that this reference voltage is 1 volt. Let's just say. So that 1 volt right there represent the desired output voltage. How so? By setting the right resistor combinations, right? As we know, for voltage divider, right? V mid, which is equal to V out prime, the sample output voltage, must be equal to R top over R bottom plus R top, right? Times V out, the actual V out, right? So you can see that if I know what I want, right? This is basically defined to be your Vref. So that's equal to Vref, the reference voltage, right? So set it to equal to the reference voltage. So if your reference voltage is 1 volt, then this V out prime or V mid should be set to be 1 volt as well, right there. Right? Okay, so then you know the Vref from the controller, right, which is constant value, and then you know V out that you want, let's say 5 volts or whatever it is, right? And then the two unknowns is R top and R top and R bottom, right? But that's easy, right? You just pick one, and then you get one unknown. Okay. So let's say let's say the output voltage is 5, Vref is 1, and I pick R, let's say R top to be 1K or something like that, right? Or let's say 10K. Then you get, the equation is following the first equation I have up there, it's going to be 1 volt equals to 10K over R bottom plus 10K times P out, which is 5 volt, and that's it, right? So you can see that there's only one unknown, which is R bottom, right? So that's like the mechanism on how to set the output voltage, right? It's very simple circuit network, and um, the difficulty is not actually setting up this part. The difficulty is setting up the compensation. We'll talk about that in this chapter next week, right? But that's basically how it is, right? So you get the sample output voltage by setting up the proper resistor values, right? You have the reference voltage, and then the output of this, right, goes through more circuitry, right? PWM circuitry, right? That's a box that we also discuss in this chapter, right, next week. And the output of which gives you the pulse, the proper pulsing with a required duty cycle. Okay. Now, of course, in the actual implementation, you're going to have a high gain amplifier, right? So the difference between the two, right? You should amplify the gain because the signal might be very small. So you have to amplify it. So you have to have a feedback, some kind of feedback like this, right? Okay. Now, just having this type of circuit is not going to be enough. This is, as you can see, this is inverting. Sorry, this is actually non-inverting. No, it's actually inverting amplifier. Sorry. This is a comparator, and then you have a high gain feedback, RF over R top, right? That's the gain. If you just have this simple feedback amplifier, then it may not be enough, right? Or most likely it's not going to be enough. The reason being the change, right, could be sudden, right? So it could be a step change, and that could cause problems, right? If you just have a gain, it can cause you overshoot, right? Percent overshoot that's going to be too high, right? Or it could cause long oscillations, right? Remember from 302, if you have, what do you call it, underdamped response, which you will, because the load is typical. That happens when the load is light. When the load is heavy, sorry, when the load is heavy means resistor is very small, right? That corresponds to small damping, and that would cause overshoot as well as oscillations. Now, with converters such as this, you have switching, right? You have turn on and turn off, a switch that turns on and off, and you have inductor. Imagine if you have oscillations, then that oscillation is going to take a while to recover, right? Because again, that switch is not on all the time. You interrupt the current, and then you let it flow, and then you interrupt again, right? So it takes more time to recover from the oscillations. Coupled with this inductor, right? Inductor is very sluggish, right, in terms of recovering from oscillations. So my point is that just by having a feedback resistor will not be enough, right? And so we're going to learn about in this chapter how we can add compensator, right? Instead of just pure resistance, we should also realize that that's not going to be enough. We're going to have to implement what we call compensator. And so there is a different type of compensators. We have type 1, type 2, type 3. And so we're going to learn about those in this chapter. Okay. Now, in practice, I'm going to use different color. Let's say green, maybe, right? The controller that you pick must be able to provide or facilitate what I need for the signal to come in from the output, and also for the feedback to provide the feedback path right there, right? The feedback. So there is, I'm going to make big dots right there. That would be one pin, right, of the controller. Usually it's called FB pin. And there's another pin right there that controller typically provides. That's typically called comp pin, right? And the rest of circuitry, they put a lot of logic circuits inside the controller. And then there's also output, right here. Sometimes they call it, they call it many names for that one. TG or bottom or BG or just gate, right? So that's basically what's going on with the controller, right? So you have a controller that takes in signal from the output of the converter, and then provide a feedback pin, so to allow us to introduce feedback circuitry. Of course, this R is going to be outside, not inside, right, of the controller. And so if you look at the book right here on the first page, notice I have the buck converter, the same buck converter, right here. That's the buck converter. Then I just draw, right? You can see the output is being monitored, right? That's a sensor right there. The output is being monitored, and this is our controller, by the way. Our controller is from Texas Instruments, TPS 4200, right there. Has 8 pins, right? And you can see the output goes back into the controller through the feedback pin. Remember the feedback pin, right there? It goes to the feedback pin, right? And here's the voltage divider. This is what I called R top in the previous page, and this is what I call R bottom, right? And out of the two, which one affects the gain of the feedback amplifier? Anybody? R1 or R2? If I go back to this page, you can clearly see which one is affecting the gain of that feedback amplifier. Which one? R bottom or R top?
I think it's R bottom.
Okay. The answer is R top, right? Because that's the path right there, right? You see the path from the signal? It goes from here, R top, into the controller. When it goes to the controller, it sees R top. Does that make sense? Right. If you compare it with a picture, right? If I just draw a picture of the op-amp amplifier, it's going to look something like this, right? Like that, right? So here's the output. Here's the, actually no. Is that, did I draw it correctly? No, I don't think I drew it correctly. Sorry. That's the wrong picture. So it's going to go from here. There you go. From here, here, and like that, right? And then this is the length, and then that's the midpoint. Yeah, that's the midpoint. Something like this, right? So you can see the gain is going to be from RF to R top, right? It's this portion right here. Yeah. Okay. So that's why you'll see later on as well in compensator or transfer function, the one that goes into the gain of the transfer function would be R1, right? And then that's the feedback pin, as you can see, right? You can see it goes to the feedback pin right there. That's the voltage divider. And then the other ones is the comp pin right there. Right? That's the one that facilitates additional circuit called compensator circuit for us to add, right? So you can see that's the pin right there, right? As you can see, it is connected to the op-amp. Remember, there is an op-amp inside right there, right? So it's connected to that. And this is type 3 amplifier. You can see there's a network right there. There's a compensator connected to the comp pin right there, right? So if you look at the block, the inside of the controller, the block diagram of the controller right here, that's provided. You can see that right after the feedback pin, when the signal goes into the feedback pin, it goes into this amplifier, op-amp, sorry, op-amp right there, right? So again, you could, if I were to redraw this, right, you have the V out right here, and then you get the the resistor divider, right, like this. This is R1, and here's R2, right, just like that. Yes, and then on the comp pin, you see you have capacitor and resistor, right, connected to the middle point, right, connected to here, basically, connected to there. And then you have more stuff there too. You have RC across R1 as well. See R4 right here and C6 right here. You can see that we have additional circuit in addition to just a pure gain. Now we have compensator as well. And this compensator is this compensator. These are the compensator for this example. Okay. Okay, how do we design this compensator? That will be this chapter. Okay. Any question on this? Right. And you can see the op-amps right here. And that's the feedback right there. Right. And there's the reference voltage. Remember I talked about reference voltage earlier? You can see easily from this block diagram that the feedback, sorry, the reference voltage is 0.7. I use 1 volt as an example, but this one is 0.7. Right? And you can see there's the output of this comparator with the compensator and the gain. It goes into PWM circuit. That would then go out to the gate drive. So that's the pin that would go to the gate of the MOSFET. Right?
How is that reference voltage normally generated?
Oh, there is a reference circuit that they use. They have a method on doing that. I don't recall exactly what kind of circuit, but they do have referencing circuit that would give us almost constant voltage. So I don't recall right now what circuit, but I can get back to you on that one.
Okay, thanks.
It's not just a power supply like this, of course. Okay. But they do have a circuit to do that.
Right. It seems like kind of like a diode or something could give that kind of voltage drop, but I know it's not quite like that.
No, it's not. Yeah. It might be related to shunt regulator, right? But I can get back to you on that one. That's a good question. That's something to actually good to add, right? Just to show what this actually is inside the controller. Okay. Any other questions? No. So the following sections, we're gonna go over body plots. We need to review body plots. I'm just gonna do this briefly next time, but the focus here is that the three main things that we're gonna be looking at is, what's called a pole, a single pole, a single zero, and So let me just write it down. Single pole, a single zero, and this last one, I'm not sure if you've heard it before. It's called the right half plane zero. Anybody heard about this before? Right hand plane zero? Yes, no? You've heard about pole, right? Zero, but right hand plane zero is a very interesting component in the body plots, right? Just briefly, and then we can adjourn. Briefly, if you have a pole, right, and in a body plot, right, how do you represent the response of a pole? Well, you have the gain plot and the phase plot, right? The gain and the phase plot. For the gain plot, if it's passive circuit, no opens, then typically the response would be this is of course frequency, right? Frequency. This is a degree angle. Degree angle. How do you? There you go. Degree angle. So at low frequencies, it's going to be zero 0 dB, right? And then when it hits the pole locations, pole frequency, let's say it's F naught, then it's going to go down, right? By what is the slope? Minus 20 dB per decade, right? For phase angle, if let's say that's the pole locations, then what happens is that it starts from zero as well, and then at the pole locations, it is going to be about minus 45 degrees. Right? It's actually equal to minus 45 degrees. And then at very high frequency, it's going to be minus 90 degrees, right? And this is typically defined to be 0.1 a decade before and a decade after, right? But if you have a zero, then what you have is this, right? Same thing, start from, if you have a zero, then the gain plot will be the same thing. You start from zero, right? 0 dB. And then what happens after, once it hits F naught, it's going to turn up, right? Instead of down, with a slope of plus 20 dB per decade. The angle is also similar, except it's the opposite, right, of a pole. So it starts from zero again. When it hits the frequency of the zero, right here, then it's going to go to 45 degrees, right? Plus 45 degrees. And then at high frequency, it's going to go to 90 degrees, right? So it's going to go something like this. It's the same thing, right? It starts to go up at a decade before the zero frequency, and then it stops. The slope stops, and it goes flat at a decade after, just like that, right? Now, what about right-hand plane zero? Right-hand plane zero. Let's use black maybe. Huh? It would have the same gain as zero. So it's going to be exactly the same as this, right? Just like a zero. However, the angle follows that of a pole. So it actually follows the pole, like a pole angle. See that? So that's the unique thing about right half plane zero, right? The gain looks like a zero, but then the phase plot looks like a pole. Gain looks like a zero, angle, phase angle, Looks like a pole, right? Now, in power electronics, in DC to DC converter, we have a converter that exhibits right half plane zero condition, and I'll explain to you next week on Monday, which is quite interesting, because that's going to be confusing to controller, because the gain is going higher, the gain is going up, but then the angle is actually going the opposite way, right? The phase angle goes the opposite way, even though the gain goes up, right? So again, I'll explain about it on Monday. Why not care about right half plane pole? Any reason why we don't care about this? Why care about left hand plane pole, left hand plane zero, right hand plane zero? Why not right half plane pole?
That's an unstable.
Yes, exactly. Exactly. So that's out of the question, because we know as soon as we have just one right half plane pole, then the system will be unstable, right? So that's what I have right here. Review of the body plots. I strongly recommend that you read this first before Monday. Review the body plots sections before Monday, and then we'll talk more about the right half plane zero. Right there, you can see the gain is positive, but the angle is negative. The angle is going down as the gain goes up.